All right, friends, we're going to start today by talking about. Actually, I should tell you, I'm switching from my large Sharpie to this fine tipped thing. I'm hoping it's going to show up on the camera okay. Um, but I guess we'll see. If this turns out terrible, I'll scan these pages at very least. Okay, so we're going to start today by talking about pressure. That's coming through well enough for me to keep trying. Let's just see how this goes. Pressure and flow rates in GC because it's one of the factors that is the most different than when you're working with liquids in liquid chromatography. So first thing you should know is that in GC, our stationary phase is an immobilized liquid. We're going to talk a lot more about the structure of this stuff a little bit later on, but for now, understand that our stationary phase is liquid, while our mobile phase is a gas, and this is what we're going to be talking about for the next little while, is the mobile phase gas, which we often call the carrier gas, right? The carrier gas. Okay, so another thing you should know is that technically speaking, literally speaking, all of our fluid flow equations still apply to gas. And so these are equations like Hagen-Poiseuille, right? The Hagen-Poiseuille equation still technically applies to gas. I'm saying technically, we'll see why in just a second. Still applies to gas. Darcy's law still applies to gas. If you know the properties of the material, you know the viscosity or the density, you're good here. The equations that describe diffusion in a fluid, which is like Einstein's equation, or there's the Stokes-Einstein relation. We talked about both of these, I think, this semester. All of these still technically apply to gases. If you find yourself in a situation where you have a flow system or a gas fluid system where the density and the viscosity of the gas are constant throughout the system, you can plug in your known factors into something like Hagen-Poiseuille for viscosity, and you can get pressure and volumetric flow rate relationships. That's great. Here's why it's not so straightforward for us. It's not so straightforward in GC because in GC, we generally don't have constant density of the gas. It's generally not constant throughout the column. And because that density is not constant, the viscosity is generally also not constant throughout the column. And that means that for our purposes, although these all still do physically apply to gases, they don't really apply very well to GC. Let's see what I'm talking about. So imagine you have a GC column. It's a long cylindrical column. We talked before about these things getting up to 100 meters long, so it's very, very long. You're going to send some gas flow in the front of this thing by pressure. We'll call this pressure at the inlet. Let's call it inlet pressure, P sub I. And gas is going to come flowing out the other end at its outlet pressure. If this is just subjected to the room, this is whatever pressure you have in the room. This is whatever pressure you're applying from, say, a regulator on a gas tank. So let's call this our outlet pressure. And the reason that density and viscosity are not constant is because unlike fluids, gases are compressible. That's how we get so much gas into a gas cylinder in the first place, which is probably where this gas inlet's coming from, right? So we're going to apply some pressure to push gas through this thing, and what we're going to find is that up here in the front, when you have a lot of back pressure applied from the restriction of this column, we're going to get more compressed gas here up front at the head of the column, And that more compressed gas is going to lead to a lower linear velocity, right? Basically, the potential energy from our pressure is going to go not into moving this stuff, but into compressing it into a smaller volume. As you get towards the outlet pressure, we're going to have less compressed gas, right? So out towards here, towards the end of the column, we'll have less compressed gas, our carrier gas, and that's going to give higher linear velocities. So the thing you should know is that despite having lower velocity here and higher velocity here, it's a matter of compression, not a matter of amount of stuff. In other words, mass is still conserved. And that should not be a surprise to anybody. We're going to say mass is conserved. Of course it is, because that is a law of nature, right? Conservation of mass. So the same amount of stuff is coming in and going out. The fact is that as a function of pressure and compressibility, it's going slower here and faster here. What that sets up is I'm continuing on here under the assumption that you guys can read all this stuff from my smaller marker. I hope that's a good assumption. But what this sets up is a non-linear velocity profile. Throughout the column. And we know that this is going to cause a little bit of complexity, a little bit of trickiness for us, because we know that linear velocity is a function when we talk about Van Deemter equation, right? The x-axis on those Van Deemter plots is linear velocity. So if the linear velocity is happening differently here than it is out here, we can expect band broadening to look a little different here than it does out here. Let's take a look at what that nonlinear velocity profile looks like throughout the column. So we're going to make a plot. Here's what this plot is showing. We are going to look at, on the y-axis, we're going to look at the velocity at position x in the column. So if we're going along the column, you know, the inlet is position 0, and as we get to the very end is position L, the length of the column. So the velocity at any position x divided by the velocity at the inlet. So the relative velocity at position x relative to the inlet. And on the x-axis, we're going to look at position x relative to the length of the column, right? So we start out at the inlet, position x is 0, and when we get to the outlet of the column, well, this x will be equal to L, so this will be, the outlet will happen at a value of 1. Sorry, that's a little jumbled there. So it turns out if we apply more pressure, we get a more nonlinear trend. Let me show you what that looks like. So both of these are going to start out here at 1, right? At the inlet, the velocity at the inlet divided by the velocity at the inlet is going to be equal to 1. But it's going to go quickly nonlinear like this. So let's suppose that curve applies for pressure at the inlet over pressure at the outlet as a 5-fold difference. If we had less pressure at the inlet, we're going to get this, again, nonlinear trend. Let's call this equal to 2. But the point is, the more pressure you apply, the faster this thing goes nonlinear. Let's just define some terms here. V sub x is velocity at position x in the column. Vi is velocity at the inlet of the column. Yeah, and we're actually gonna for use in the next equation here, we're gonna actually give this a definition. This Pi over P0, the pressure at the inlet over the pressure at the outlet. We're just gonna call this P for pressure. Okay, so the take-home message here: higher inlet pressures cause this nonlinearity in velocity profile to be exaggerated. So we can describe actually this curve, or rather this value, Vx over Vi, as a function of pressure. We can say basically as a function of this thing right here, how quickly does this go nonlinear? We do this mathematically this way. We say Vx over Vi is equal to p squared, that's this p right here, over p squared minus, and this is a lot of fluid dynamics that gets you here. I'm really not, I don't think it's valuable for us to go through the derivation of this thing. There's a take-home message here, which is that we have a predictable relationship. Okay, so this is Vx over Vi as a function of this term x over L. This basically describes this curve for each value of pi over p0. So we do have a very good way of predicting exactly what the velocity is at every point, and that can be useful in designing, say, a new GC column and in how we load stationary phase in there. What it's not useful for, or what it's not directly useful for us, is using in a lot of our chromatography equations, right? I mean, we don't really know how to handle these nonlinear velocity profiles when we talk about chromatography. So instead, let's think about how we turn this into an average velocity. So a good example of a chromatography term we might be interested in is, what is the void time on this column? All right, what is T sub 0, the time of an unretained species on this column? For any chromatography, liquid or gas or otherwise, it's the length of the column divided by the average velocity of mobile phase going through that column. Let's just find this. V bar equals the average linear velocity. But we don't know how to get this average linear velocity. We don't know how to get there because we only have this description of this nonlinear process. So let's say that this average velocity is going to be equal to a velocity that we can measure at the outlet of the column, right? So we measure what velocity, what say volumetric flow rate is coming out of the end of the column, the velocity at the outlet, the flow rate at the outlet. We're going to multiply this by some kind of correction factor, right? So J is a correction factor that corrects for compressibility, I guess is what we're going to say. Yeah, a correction factor for compressibility of the carrier gas. Okay, and J is also a term that has been pretty well worked out by a lot of fluid dynamics folks for the cylindrical GC columns, and it looks something like this. J is equal to 3/2 times that pressure term, right? That's our PI over P0, pressure term squared minus 1 over that pressure term cubed minus 1. All right, a fairly straightforward algebraic relationship that's going to essentially average this nonlinear velocity to give us an average velocity that happens on the column. Okay, so that's good. We have a way to, so we can get average velocity from measuring the outlet velocity and account for, so let's say this accounts, going a little too fast here. This accounts for compressibility. And that's good. And it'd be great if that was the whole story. It's not the whole story, right? Because the thing with GC is that GC is done at elevated temperatures, right? So, but what about temperature? Because we know that as temperature elevates, gases expand. And so we have these two competing things. We have the compressibility of the pressure effects as the stuff flows through the column. And we have the expansion of the temperature effects. It turns out this one's a little mathematically a little simpler. So we are going to, let's see if this will fit on this page. I don't think it will, so let's start a new page. Let's talk about compensating flow rates for temperature expansion. We're going to compensate flow rates for temperature expansion of the gas. Okay. And like I said, mathematically simpler. So we're going to say that the velocity on the column is equal to that measured outlet velocity. We're going to call this V sub m for a second. That's the amount of, that's the volumetric flow rate that we measure coming out of the column times the ratio of the column temperature to the temperature at the outlet, the temperature where we make this measurement. And I should tell you, these are absolute temperatures. That is, these are temperatures in Kelvin. So let's define some of these terms. Vc equals the flow rate on the column. Vm is the measured V sub zero. It's the measured outlet velocity. Tc is the column temp in Kelvin. I don't want us to forget that. And To is the outlet temp, again, in Kelvin. Okay, so we're almost ready to think about flow rate in terms of temperature compensation and compressibility compensation, but we don't have a nice clear way to get at this measured V0 just yet. In other words, conceptually how much flow per unit time, how much volume per unit time is coming out of that column. That's a simple concept. How do we actually measure this, right? And there are a lot of modern technologies. Hall effect sensors are really common if you can get them to work with gases. There are a lot of modern technologies used for measuring the flow rates of fluids. But I want to show you a classic, simple technique for doing this, partly because it's a very simple concept to just kind of mesh in your brain. And partly because I love things that are simple that get complex jobs like measuring that volumetric flow rate done. So the classic approach is called a bubble flow meter. Okay, so we are going to look a lot more closely at the anatomy of a GC later on, but let's just very briefly sketch out an instrument. Here's a column oven. This controls the temperature of the column. There's this extra little heated compartment called a heated inlet. This is where our sample gets injected. This is the equivalent of a 6-port injector for a GC. Again, all this anatomy we'll go over later. We have some flow of gas coming in. This is our carrier gas coming into a column, runs through our heated injector. We get 100 meters of this stuff, so it's generally up to 100 meters of this stuff, so it's generally coiled up pretty tightly inside this column oven, and then it comes out. So our chromatography happens here. Here's our the outlet of our column, and we want to measure volumetric flow rate coming out of the end of this column. So how do we do it? Classic approach, this bubble flow meter, is to take a graduated column. So this is something just like a burette, basically. Okay, and what we add to the side of this graduated column, so let's just label this. This is a graduated column or graduated cylinder. And we add like a squeeze bulb. And this is full of soapy water, right? Something really simple. Okay, so how do we use this apparatus to measure a flow rate? Well, if we have gas flow coming out of this column and we kind of squeeze this bulb lightly and inject a little soap film, what we'll see, we're going to kind of blow this up here to look more closely at that graduated cylinder, graduated column. Um, Squeezing this thing is going to put a little soap film, and we're going to get essentially a meniscus that represents a soap bubble, right? This is a soap bubble. And that soap bubble is going to rise. It's going to move at the rate of our outlet volumetric flow rate of V sub 0 because we're filling up behind that soap bubble the outlet of our column. Really simple, but if you can watch that soap bubble move and you can count how many mils it moves in how much time, you understand the outlet flow rate. So let's finish up this discussion on flow rates in GC with a little exercise. Okay, so we're going to use a bubble meter like I just showed you, and we're gonna see that the bubble rises 10 mils in 68.4 seconds. The temperature of the column is 100 degrees C. The temperature of the outlet is room temp. The pressure at the inlet is 40 psi G. We're going to talk about that G in one sec. And the question in this exercise is what is the average velocity of carrier gas going through that column under these conditions? So the first thing we need to tackle is what is this PSIG? So PSIG means gauge pressure. Okay. Gauge pressure is the pressure that you read, pressure that is read from, spoiler alert, the gauge. So if you have a gas cylinder and you set it to, I don't know, 10 psi, if you set it to, let's use our example, 40 psi on that gauge, you are actually reading on that gauge 40 psi G. So psi G is the pressure relative to room pressure, right? That gauge compares the pressure of the gas cylinder, or the pressure of the flow, whatever you're setting the regulator to the pressure of the room. But the thing that we have to remember is that we have an ambient gas pressure in the room. And so if we want a value that is in psi, right, that is psi is absolute pressure, or in other words, pressure relative to a vacuum, we have to take into account the pressure of the room, right? So psi, an absolute pressure measurement, is equal to the gauge pressure, which is often reported as psi. You know, this is one of the big mistakes that a lot of people make, is to report psi instead of psig. But in order to get an absolute pressure in psi, we need to take that gauge pressure that we read and we need to add on to it whatever the pressure of the atmosphere is. So I'll tell you that 1 atmosphere, if we just assume everything is done at sea level, which is a fair enough assumption because the variation is pretty small, 1 atmosphere is equal to about 14.7 psi. So if we take a gauge pressure, we add 14.7 to it, we get the absolute pressure in psi, and that's going to be important in this exercise. The other thing we can devise or derive from this is the idea that if we're putting 40 psi into the head of the column and the outlet of the column just coming out to the room, then the pressure at the outlet equals room pressure. If we assume that that is atmospheric pressure, 1 atmosphere, then the P outlet is 14.7 psi, absolute. Okay, so we've tackled this thing of PSIG. We understand what the pressure at the inlet. We understand the pressure now of the outlet. So the first thing we're going to do is correct for temp. Correct for the temperature. This is the mathematically simpler one, right? This is that the volumetric flow rate on the column is equal to the volumetric flow rate at the outlet that we measure times this ratio of absolute temperatures, Tc over T0. So let's get this VM out of the way. So we know, let me bring this back into view. We know that the bubble is rising 10 mils in 68.4 seconds. So VM is going to be 10 mils over 68.4 seconds. We're going to put that in mils per minute. So let's say there's 60 seconds in a minute. That gives us, just plug and chug, that gives us 8.8 mils per minute. All right, so we have a VM. The V on the column is equal to that 8.8 mils per minute. 8.8 mils per minute times our temperature correction factor here. So 100 Kelvin is going to be 3, if I remember Gen Chem correctly, 373 Kelvin. Let's give room temperature as 300 Kelvin. That's a pretty warm room. That's like 80 degrees Fahrenheit. But you know what? Let's say the air conditioning stopped working. If that's the case, then that gives us a corrected for temperature outlet volumetric flow rate of 10.9 mils per minute. In other words, in terms of volume per unit time inside that column, because the temperature is elevated, this 8.8 mils per minute that we measure at room temperature is actually expanded to 10.9 mils. That is per 10.9 mils per minute. That is actually flowing through the middle of the column because, again, temperature has expanded that 8.8 mils to 10.9 mils. Okay, that's the temperature correction. It's not the whole story because we have these two competing factors, right? We have expansion due to temperature and we have compression due to gas pressure. And so let's then, once we've temperature corrected, now let's correct for compressibility. So the compressibility correction, to remind you, is that the average velocity going through that column at all points in this nonlinear profile is equal to the outlet volumetric flow rate. I guess I should be saying the average volumetric flow rate, not the average velocity, times that correction, right? And we said J was equal to 3/2 times P squared minus 1 over P cubed minus 1. So let's put this in terms that actually apply to our example here. So 3/2 is a constant, but we're going to be looking at an inlet pressure of 40 psig. When we add atmosphere to that, that becomes 54.7 psi absolute over room atmospheric pressure 14.7 psi, and that is squared minus 1 over the same term, 54.7 over 14.7 cubed minus 1. I'm going to take this whole J term, I'm going to plug and chug it for you. It turns out to 0.38. Okay, so now let's plug back in the average velocity on this column. It's going to be equal to our temperature corrected outlet velocity, outlet volumetric flow rate rather, which we just did in the previous step, got us out to 10.9 mils per minute times our correction factor 0.38 in this case, which is going to be equal to 4.14 mils per minute. And the thing to note here is that we come out with, let's make sure that is really clear. Yeah, there we go. We come out with an effective average volumetric flow rate within the column, much less than what we measure at the outlet, or even that we measure and correct for temperature at the outlet. And that's because compressibility has this effect of making the volume smaller than it would be at atmospheric pressure.